Okay, cool. So the first thing that I want to tell everyone is that the due date was tonight at midnight. I'm changing it to Sunday because, like, why not? If you're busy tonight, but maybe you do your homework on Sunday, might as well. Sometimes I like to just say it's due tonight, so then you get it over the way and you don't have things to worry about over the weekend. But changing that to Sunday. And so we are going to spend the first 20 minutes ish, a little less of class, looking at the second article and going through that. And then the last 10 minutes of class, we're doing Black History Month First Friday All Class activity. So I'm kind of excited about that. But first, we're going to go until there's 10 minutes left, and then we'll just end where we end, and the rest will be homework. So this is the article that we are reading today. Again, as you are reading, you are taking your doodle notes, your sketch notes type of deal. If you're like, wait, what? Have a title and then doodles in order to represent the article we are reading. If you need more information, watch the video from yesterday. And then just so you know, what is actually going to be due is you are going to take a picture and insert them into this document and turn it in, or just attach the pictures, turn it in any which way. There should be two pictures, one of your doodle notes of the ionic compound properties article, and then one of the covalent compound one. So one from yesterday type of deal, one from today type of deal. But so this is the article that we are reading today. These are covalent compounds, which we have not learned about. Like, you don't even know what they are. So basically, just to show you, because just so you at least have an idea a little bit, is that, oh, I like this image. Basically, ionic compounds, the last ones we learned about, ionic bonds, one thing takes something and the other thing gives it away. With covalent, they share. So F has 7, F has 7. In order for them both to be happy, they share one of them. Each of them shares one, and then they become attached because they're each like, well, I want it, well, I want it, well, I want it. Well, we'll share, and then everybody's happy type of deal. So that is covalent. Will we get into much more detail with that? Yes, but I just wanted you at least to have an idea. So I'm going to read the first paragraph, then I will ask for volunteers to read the little bit others. And remember, you should be having a piece of paper and drawing notes as we do this. And yes, I said drawing, not writing, because you're drawing, you're doodling these things to represent what we are reading. So this is covalent or molecular compound properties. So on your piece of paper, you should probably write covalent, and maybe properties or characteristics if you want, but definitely covalent should be big and large in the middle of that piece of paper. And I'm going to read the first paragraph. So, covalent or molecular compounds contain atoms held together by covalent bonds. These bonds form when the atoms share electrons. So somehow draw that. Maybe show an electron and it being shared somehow. I don't know. Sharing is caring. Something. That is the key point. Because they have similar electronegativity values. Covalent compounds are a diverse group of molecules, so there are several exceptions to each of the following rules / characteristics that we're going to be going over. When looking at a compound and trying to determine whether it is an ionic or covalent compound, it's best to examine several properties of the sample. These are the properties of the covalent compounds. So there are definitely exceptions. Like, we have like the words most and tend and I don't know, many. So it's not like this is always true. It's not that. But as a whole, there's trends that we can look at. So I have a first paragraph here. Does somebody want to volunteer? I'll give it 10 seconds to volunteer. If not, I will pick on someone. Let me go scout out who I'm going to pick on. I know. Asia, could you unmute your mic and read this, please? Oh. Oh, no. I thought I had a chat, but that was from before. Is Asia here today? Yes, no, maybe so? Me. Okay, fine. Alexa, you can read. Unmute your mic and go for it.
Okay. Most covalent compounds have relatively low melting points and boiling points. While the ions in an ionic compound are strongly attracted to each other, covalent bonds create molecules that can separate from each other when a lower amount of energy is added to them. Therefore, molecular compounds usually have low melting and boiling points.
Love it. Thank you so much. So our key bits here, low melting and boiling points. My video. Not that one. This one. Start at 45 seconds. This is to explain that. So like, why does that happen? Why is it low melting and low boiling points? This is why.
Now, the first thing to know is that covalent bonds are really strong, which means that a lot of energy is going to be needed to break apart any atoms that are covalently bonded to each other. So if we consider a simple molecular substance like chlorine, the atoms within each molecule will be strongly bonded together. However, in order to melt or boil chlorine, we actually don't break these strong covalent bonds. Instead, we only need to break the weak forces that exist between different molecules, which we call intermolecular forces. Because of this, we only need very low temperatures to melt or boil simple molecular substances. For example, chlorine boils at minus 34 degrees Celsius.
So just to like explain that, we're not breaking these apart when we boil things or melt things. Ooh, there's like a bunch of these that are combined, like a bunch, like here. And what we're separating is like those combined from each other. It's not like these two are separating. It's like these two are separating from these two are separating from these two, but these two are not separating from each other. So hopefully that makes a little bit of sense. And so that's why it's low temperatures, is because the forces between these are weaker versus between. Yeah, hopefully that's not too confusing. There's a lot of between things, but so that is that. So within your doodle, things you might want to include. How can you represent low melting and low boiling? So that would mean that those are really cold, right? Like low melting points and low boiling points. This thing boils at negative 34 degrees Celsius. So it's like water turns to ice at 0 degrees Celsius. So it's even colder than that, and that's when something boils. Okay, so just so hopefully that makes a little bit of perspective, but I'm gonna keep going. And we're not pausing today because we are only having our 20 minutes, so you can catch up on your doodles at the end if you need to, or go back or do what you want. We're skipping this second bullet point. Okay, so on to this third one. If Omar's here, I'm gonna have him read. Omar! Wait. Yeah, Omar. Omar, can you unmute your mic? And read this paragraph.
Covalent compounds tend to be soft and relatively flexible. This is largely because covalent bonds are relatively flexible and easy to break. The covalent bonds in molecular compounds cause these compounds to take form as gases, liquids, and soft solids. As with many properties, there are exceptions, primarily with molecular compounds assume crystalline forms.
Awesome, love it. So for this, I do not have a video, but on your sketch notes, we want things that are soft and flexible. So think about, okay, what is soft? Like literally, like if you feel something, like that could be what jogs your memory in terms of like what is soft. And then flexible, what are some things or people or whatnot who are flexible? Maybe like gymnasts. Draw a balance beam. I don't know. Or like a rubber band. So things that are flexible to help in your mind be like, okay, covalent compounds tend to be soft and flexible. So in terms of like thinking about it, like okay, What does that mean? An example that came up when I was trying to find a video was pencils and graphite. So like if you write with a pencil, like that comes off very easily, right? You're not like having to put a lot of effort into like scraping off the writing, the tip. You know what I'm saying? So like that would be an example. So graphite is a covalent compound, and that's kind of showing like the softness of covalent compounds. And then this exception down here is this crystalline forms. An example of this is diamonds. So diamonds have are covalent compounds, but they assume this crystalline forms, and diamonds are not soft or relatively flexible, right? Definitely not. So there are exceptions, like I said earlier. Okay, so this is our next one. Let us go with Valeria. Are you around, and can you unmute your mic and read this one, please? It is highlighted. Kevin keeps leaving our meeting. I think he's scared I'm going to call on him. But Valeria, are you here? Yes, no, maybe so. Okay, if not Valeria, then I'm going to Kaylee. Kaylee, can you read the highlighted passage?
Okay. Covalent compounds tend to be more flammable than ionic compounds. Many flammable substances contain hydrogen and carbon atoms, which can undergo combustion and reaction. The releases energy when the compound reacts with oxygen to produce carbon dioxide and water. Carbon and hydrogen have comparable electronegativity, so they are found together in many molecular compounds.
Love it. Awesome. Thank you so much. And I did try finding a video on this, but there's no videos that are like less than 10 minutes long. It's very detailed, and you have to understand a lot of things in order to figure this out. But so basically, covalent compounds tend to be more flammable than ionic compounds. One example I have for you here, nail polish remover. On here, it literally says, warning, extremely flammable. Keep away from flame. So I don't know if you can see that, but it says that. So extremely flammable. Another one would be like lighter fluid. I've been trying to think of the name for that for this, like my last two class reads. Lighter fluid. That's easily flammable and a covalent compound. So moving on. Okay, these last two. Let me see here. Okay, decent on timing. I am actually going to read this last one because, well, unless there's a volunteer. Somebody wants to read, unmute your mic and do it. Otherwise, I was planning to. And yes, Omar, Kevin definitely just doesn't want to read. That's why he keeps leaving. 100%. Just kidding. I don't know. I assume. Okay, I'm just going to read it. So many covalent, and I'm switching the order of these last two. So we'll get to this one, but first I'm reading this one. Many covalent compounds don't dissolve well in water. There are many exceptions to this rule, just as there are many salts that don't dissolve in water. However, many covalent compounds are polar molecules that do dissolve well in polar solvents, such as water. Examples of molecular compounds that dissolve well in water are sugar and ethanol. Examples of molecular compounds that don't dissolve well in water are oil and polymerized plastic. So don't dissolve well in water. So maybe you draw water with some chunks in it, things that are not dissolving, they are not disappearing. However, when they do dissolve in water, so do they dissolve well in water? No, but when they do, they don't conduct electricity. So I'm going to read this one as well, and then I'm going to show the video. Ions are needed to conduct electricity in an aqueous solution. Molecular compounds dissolve into molecules rather than dissociating into ions, so they typically do not conduct electricity very well when dissolved in water. So now I'm going to show my video. And this is kind of combining both of them a little bit. So this is salt on the left, and this is ionic. We're not dealing with that. He'll reference it a little. We're looking at on the right, this is sugar. And so this is a sugar covalent compound up top, and a little too far. And then on the left, this is like a bunch of sugar molecules that are like pushed together type of deal. So we'll see what happens.
Here's our grain of sugar. It goes in the water, we dissolves. Okay. Now let's take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms. So, to answer the question, what does it look like when something dissolves in water? The short answer is, it actually really depends whether you're talking about an ionic compound or a covalent compound. If it's an ionic compound...
Okay, that was enough. I went a little extra. So, how is this relating? Our first things is that most don't dissolve well, meaning they wouldn't even break up like how that did. But this was sugar, so it says this is that dissolve well, this is sugar dissolves well. And then our other thing is when they're dissolved in water, they don't conduct electricity. Ooh, I only have a minute. They don't conduct electricity. Reason being is over here with our salt, it breaks up into positives and negatives and positive and negatives. This is our dissociated ions. They are splitting up and then charges can flow. Versus in the sugar, these molecules still stay together. Like they separate from each other, but one of these things is a like complete sugar molecule. So those don't split up and create charges. It's still like a full kind of thing. I don't know if that made any sense, but that's what we got. So, your, like I said, homework. And down here, there's some exceptions, learn more. So you might need to go through and kind of like fill in some gaps in your notes because I know that was quick. So that is like your homework for Sunday. That one, as well as the ionic properties. If you didn't finish that one, you got to do that one. So that is where we're at with those. The rest of today, we have 10 minutes, is consisting of this. So I'm sharing this link. Let me copy. So basically, I was thinking that each Friday in February, yes, copy link, we will do something to honor / learn about / celebrate / focus on Black History Month, because that is February. This Friday, we are going to take the last 10 minutes of class, which is happening now, to look up and learn about different Black people / heroes / extra impressive people that you think everybody should know and learn about. So you write their name, you write a link. You don't need to. I just did too because I did. But what they're known for. And then optional, if you want to tell me why that person is great, tell me. If not, if you're like, you'll get it when you read it. Like, that's fine too. And so that is what we're doing. Oh, I didn't share the link. But, so click on this link. You got 10 minutes now. You got to pick person, put them in here. Mine, if you need more guidance here, mine is Neil deGrasse Tyson. He's awesome. He's a scientist, astrophysicist. This TikTok is explaining him explaining humans and the universe, and it's just, I love him. Anyways, so, and it can be anybody. Oh, it can be, actor, actress, singer, historical person, someone who's dead, someone who's alive, politician, anyone who you're like, this person is impressive and should be recognized. Who is Black, because we are honoring Black History Month, obviously. That is a given. But so yeah, that's all I have. I'm gonna pause this recording.